Good afternoon, class. We are looking at Chapter 4, Application of Derivatives, Section 4.4, Optimization Problems. We covered 4.1, maximum and minimum values, 4.2, how derivatives affect the shape of a graph, and now optimization problems. First, reminding you of various differentiation formulas from the definition to power rule, trigonometric functions, product, quotient, chain rules, exponentials, logs. And now if you have a function y equals f of x and you have 2 points P and Q, the run or delta x or dx or bp along the x-axis, and the rise, it's either along the curve, which we call it delta y, which is f of x plus delta x, this distance, minus f of x. And that's, in other words, the distance of BQ, which is different than rise along the tangent line, which we call it dy or f prime of x dx ab. Also, linearization refers to finding equation of a tangent line. Reminding you of the following. Local minimum occurs at the point C in an open interval of a to b in the domain f of c less than or equal to f of x for all x values in the open interval. Local maximum occurs at the point C in an open interval a to b in the domain if f of c is larger than or equal to f of x for all x values in the open interval. In other words, we have the peaks, local max, valleys, local mean in some open interval. On the other hand, absolute, also known as global extreme, absolute minimum occurs at the point C if f of c is less than or equal to f of x for all x values in the domain. Absolute maximum occurs at the point C if f of c is larger than or equal to f of x for all x values in the domain. In other words, local mean, local max, local mean, local max, local mean, local max. This local minimum is also absolute minimum because no other point has a smaller y coordinate. This local max is also an absolute max because no other point has a larger y coordinate. Critical point, how do we find them? A critical point of a function f is a number c such that f prime of c is 0 or does not exist. What is the process? Number 1, find f prime of x. Number 2, set it equal to 0. Number 3, f prime does not exist. Also, we have the extreme value, also known as closed interval theorem. If f is continuous over a closed interval of a to b, then f has a maximum and minimum value over that interval. The methodology is verify that f of x is continuous on the closed interval of a to b, find critical points by setting f prime equal to 0 doesn't exist, find the functional value at the endpoints a and b and the critical points. Absolute maximum is the largest and absolute minimum is the smallest value. Very straightforward, everybody. Also, how derivatives affect the shape of a graph. Reminding you, theorem, a function is increasing when f prime is positive, decreasing when it's negative. So increasing, decreasing. A relative maximum or relative minimum is a critical point at the top or bottom of an interval of a graph, peaks and valleys. A function is concave up where f double prime is positive and concave down where f double prime is negative. Concave up, concave down. An inflection point, short IP, is a point where concavity changes. Inflection points occur where f double prime is 0 or f double prime does not exist. So the change occurs. And now, new stuff, 4.4, optimization problems. Optimization problem is the problem of finding the best solution from all feasible solutions. In other words, find a solution in the feasible region which has the minimum or maximum value of the objective function. Examples, we want to maximize profit, minimize cost, maximize area enclosed, etc. The first derivative test for absolute extreme values. Suppose that C is a critical number of a continuous function f defined on an interval. If f prime is larger than 0 for all x less than c, and f prime of c is less than 0 for all x less than larger than c, then f of c is the absolute maximum. And if f prime is less than 0 for all x less than c, and f prime is larger than 0 for all x larger than c, then f is the absolute minimum value of f. In other words, the local becomes absolute if we are talking about the entire domain. But here's what makes it easier to understand. The first derivative test, dt, for absolute extrema. A local extremum is an absolute one if it's the one and only extremum. In other words, you have an interval, you have an open interval, and you have only one critical point. Local becomes absolute, whether you go with the first or the second derivative test. The second derivative test for absolute extreme on an interval, if there is exactly one, and that's really the key, one critical number. Let f be continuous on an open interval of a to b. We're talking about open interval and one critical point. With only one critical number c in the interval, if f prime is positive, is 0, and f double prime is positive at c, then f of c is the absolute maximum on the interval of a to b. Because if it's positive, it's concave up and it becomes the minimum. If f prime of c is 0, that means that's a critical point, and f double prime of c is negative, then f of c is the absolute maximum, because negative means concave down. It's the maximum of f on the open interval of a to b. So that's the idea behind how we use the first or the second derivative test. In short, one critical point in an open interval, local becomes absolute. So here's the first example we want to look at. A farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. What are the dimensions of the field that has the largest area? Well, you can make up some examples. For example, 100, 100, 2,200, their product is 22,000, so on and so forth. But this is really not the proper way of doing that. What is the proper way of doing that? You draw and you define your variables. The width is x, the length is y. You want the largest area. You want to maximize the area equals x times y. We have 2,400 feet of fencing. That is the constraint. That's the restriction. And so if we want to find that, the perimeter of a rectangle is normally 2 times the width plus 2 times the length. So 2 times x and 2 times y. However, since we don't need fencing here, is 2x plus only 1y equals 2,400. So the objective, maximize the area equals x times y. Subject to constraint, 2x plus y equals 2,400. A is a function of two variables, x and y. Subject to constraint 2x plus y equals 2,400. We are going to use this and solve for one of the variables. Obviously, we're going to solve for y. And if we replace the y with that, now a becomes a function of one variable, namely x. So we're going to write a of x is x times 2,400 minus 2x. Now, we need to find our domain. Remember, x represents dimensions, must be positive. Also, If you set this one equal to 0, x becomes 1200. So if you choose x to be larger than 1200, this becomes negative. Negative times positive, area cannot be negative. So your restriction domain x is between 0 and 1200. Y larger than 0, dimension. Y less than 1200 because makes it negative. And so to move on to the next part, for the sake of differentiation, I'm going to distribute first, and I'm going to write 2400x minus 2x squared. I want to find the critical point, so I am going to differentiate this. A prime of x becomes 2400 minus 4x. When I set it equal to 0, I get 600. So here's what happens. Let me erase my work. We have an open interval of 0 to 1200 with one critical point, and that is telling us that local becomes absolute. Whether it's local max or local mean, we don't know, but we know it's absolute because it's only one critical point. So how do we do that? The first or the second derivative test? I'm going to do both because I want to show you how it works, and then we take it from there. Having said that, if I want to do with the first derivative test, I need a number line from negative to positive infinity. I put the critical point 600 here, and I choose the test point on the left and right. I pick up two numbers, and I'm going to evaluate A prime. So what happens is that at 600, A prime is 0. To the left of that, if you plug in, pick, for example, 0 and plug in, you get 2400 positive. To the right, for example, I don't know, 1000 minus 4 times that is minus 4000. 2400 minus that is negative. So positive and negative means increasing, decreasing. So as we move on from increasing to decreasing, it creates a local max, local max. However, we said there is only one critical point and an open interval local becomes absolute. That's what we were explaining in the previous paper. And we're done with that. However, I want to show you the second derivative test most of the time works better. So what is the second derivative test? A prime is given, find A double prime is simply -4. The second derivative test says, okay, plug in the critical point and see if it's positive or negative. Because A double prime is a number, it doesn't matter positive or negative, then it makes no difference what number you have. It doesn't change the fact that this is negative. So it's always negative. Negative means concave down. Concave down means maximum. Why? Because it looks like that. So maximum occurs when x equals 600. And as I mentioned, this is local and it becomes absolute. So when x equals 600, what is y? We go back to 2x plus y equals 2400. We go to the constraint, replace the x with 600, 2 times that 1200, subtracted from 2400, and y becomes 1200. So what is the largest area, the maximum area, x times y? That means 600 by 1200 is 720,000 square feet. That's the largest area, everybody. Find two numbers whose sum is 80 and whose product is a maximum. We have to define our variables. What are those numbers? How about x and y? What is the objective? Maximize their product. P equals x times y. I'll call it P for product. Call it anything you want. F. Subject to the sum is 80, x plus y must be 80. So that's the constraint. Again, same situation. P is a function of two variables. We want to maximize that. We want one variable. So we are going to use the constraint and solve for one of the variables, in this case for y. Replace it here and you get P of x. Now P becomes a function of x if I replace the y, and I get x times AD minus x. Now, what are the restrictions on x? In other words, what is the domain? I'm going to go back to question. So the sum is AD and we want to maximize the product. That means we are hoping the product is not negative, is not even zero. So we are hoping the product is positive. So if I want the product to be positive, I want x to be positive, and I want AD minus x to be positive. In other words, x has to be positive, and then AD minus x equals 0, x equals AD. So if I choose x larger than AD minus x becomes negative. So it has to be less than AD. So x is between 0 and AD. This would be appropriate. Again, remember, we want to maximize. If we were to minimize, would be a different story. So having said that, to move on to the next section, I'm going to distribute and I get ADX minus x squared. So I get it ready for critical points. To find critical points, we're going to differentiate P, becomes P prime, which is AD minus 2x. Set it equal to 0, x becomes 40. So we have an open interval of 0 to AD with only one critical point. So local becomes absolute. So how do we deal with that? Very simple. We are going to go with the second derivative test because we can easily see P double prime is -2. Remember, you have to plug in x, but it's independent, so just is always negative. Negative means concave down. Concave down means max. Why does it mean max? Because it looks like that. So maximum occurs when x is 40. Put it into this. X plus y is 80. Y must be 40. And what is their maximum? 40 times 40, 1600. So that's pretty straightforward. And I hope you realize that the second derivative test makes it fairly nice and easy. A farmer with 240 feet of fencing wants to build an E-shaped enclosure besides a creek. As seen in the diagram, find the maximum area that can be enclosed. And I can't emphasize this enough. Either they give it to you or you have to figure this out. This is important. And now we have to define our variables. So the width is X, the length is Y, area, we want to maximize the area, which is the width times the length, or xy. And we have only 240 feet of fencing. This distance is x, so is this, so is this, and I'm going to write This is x, this is x. So we have 3x and 1y. They add up to 240. Again, a is a function of two variables. To make it a function of one variable, we're going to solve for y, and we make it 240 minus 3x. And now I'm going to replace the y with 240 minus 3x. I need to know what is the domain. Obviously, x represents dimension must be positive. Also, if you set this one equal to 0, x becomes 80. And class, if I choose x to be larger than 80, then this becomes negative and we can't have it. Therefore, x is between 0 and 80. And having said that, to get ready for the next step, I'm going to distribute. I get a of x equals 240x minus 3x squared. I want to find the critical points, so I'm going to differentiate. 240 minus 6x. When I set this equal to 0, x becomes 40. And so I have an open interval with only one critical point. That means local becomes absolute. Is this a max or is this a mean? Let's find out using the second derivative test. If this is a prime, a double prime is simply -6. Negative, remember, we have to plug in 40, but this is independent of that. It's always -6, which is negative, which is concave down, which is maximum, because concave down looks like that. Maximum occurs when x is 40. So what is y? I put the 40 here, 3 times that is 120, subtracted from 240, and I get y equals 120. So what is the maximum area? The product of 120 and 40, which is 4,800 square feet. A box with a square base and open top must have a volume of 32,000 cubic centimeters. Find the dimension that minimizes the amount of material used. So let's discuss a couple of items from prior knowledge of mathematics, algebra, geometry, reminding you this is called a rectangular solid or prism. Here's the length, here's the width, here's the height. If you multiply the three, you get the volume. Surface area, the concept of gift wrapping, this has 6 sides. So the one facing us, the area is length times the height. We have one in front, one in the back, so there are 2 of them. On the side, the width times the height is the area. We have one on the left, one on the right. We have 2 of them. The bottom, the base length times the width, we have 2 of them. The top and the bottom are identical, so that's why we have these 2. Now, if all sides are identical, we call them a cube, in which case the volume is s cubed. Surface area, one side is s squared. There are 6 of them, 6s squared. So this is just to remind you how we did this before. Again, prior knowledge of mathematics. What's happening with this one? We have to define our variables. Because it's a square base, these two are the same. So x times the height. Now, so we have defined our variables. We want dimension that minimizes the amount of material gift wrapping. So let's find the surface area. First, the one facing us has the area of x times h. And because the base is a square, all four sides have the same area, x times h. So we have 4x times h. The bottom has the area x squared. So does the top. So normally, the surface area for this one would be 4xh plus 2x squared. But this is open top, so only 1x squared. Okay. Subject to 32,000 cubic centimeters of volume. What is the volume? X times h. In other words, x squared h. So subject to constraint, the volume is x squared h, 32,000. We are in business now. As you can see, the surface area is a function of two variables, x and h. The constraint volume is x squared h. We're going to solve for h. That means divide by x squared. Now, for x times h, we're going to replace the h into s function, and it becomes a function of x. So s becomes s of x when we replace the h. Now, x cancels out this exponent. We get 4 times 32,000, 120,000 divided by x plus x squared. Because we want to get it ready for the next step, which is differentiation, we are going to rewrite this as 128,000 x to the power of negative 1 plus x squared. And x represents dimension must be positive and there is no other restrictions. So we're going to differentiate this. S prime of x. In order to find critical points, we're going to differentiate this. S prime of x is negative 128,000 x to the power minus 2 plus 2x. Now, in order to find the critical points, you look at where S prime is 0, where S prime doesn't exist. To do so, we are going to rewrite this in the following manner. Negative 128,000 x to the power minus 2 is the same as negative 128,000 over x squared. I'm going to take a common denominator, which is x squared. This doesn't change, and this becomes 2x cubed. So now you have S prime of x. S prime of x is 0 if the top is 0. S prime of x doesn't exist if the bottom is 0. The bottom is 0. X is 0, is not part of the domain. So S prime is 0. That means the top is 0. And to solve this, two x cubed is 128k or 128,000. X cubed is 64k and x is 40 units, centimeters. Very straightforward. So we have an open interval with one critical point, which means local becomes absolute. So what is this? Max or mean? Well, we're going to go with one of the tests, first or second derivative test. I want to go with the second derivative test. To do so, I'm going to differentiate this one. The product of these two is positive 256,000 x to the power minus 3, and this is plus 2. According to the second derivative test, you have to plug in the critical point into S double prime and observe if it's positive or negative. So when we plug in, this is x cubed at the bottom. So 256,000 over 40 cubed plus 2. Now, you don't even have to evaluate to notice this is positive. So is this one. So it's positive. That's all we want. Happen to be 6. Positive means what? Concave up. Concave up means what? Minimum. Why minimum? It looks like this, everybody. So minimum occurs when x is 40. So if I put it here, 40 squared, that means 1600 times h must be 32,000, and I get h to be 20 centimeters. So the dimensions are 40 by 40 by 20. 40 by 40 by 20 units centimeters. Now, we wanted the dimensions and we are done. They didn't ask for this, but the surface area, 4 times x times h, 4 times 40 times 20 plus 40 squared. If anybody asks, it's 4,800 square centimeters, everybody. That's the final answer. So x equals 40 will maximize.